Welcome back. In this lesson, we're going to look at the very beginning ideas in chemistry. We're going to eventually need to study rocks, and rocks are combinations of matter. So atoms have been fused together in order to form everything that we see, and the minerals then make up rocks, and all kinds of rocks are made out of different things. So we're going to need to look at how these things come together, how ionic bonds work and in making minerals. So to do that, we're going to look at the very beginnings of chemistry. So we're going to look at matter today. We're going to look at the smallest parts of matter, the smallest little Legos that make up everything, called atoms, the various forms of those atoms, which are called the elements, and then the subatomic particles that make up those atoms and how they work. So very interesting study. And just the very beginning, so I hope you like it. Okay, so in Chapter 4, we're going to begin geology, which is the study of rocks and minerals. And minerals are put together by different atoms and ions and connection and energy, and all of that is chemistry. So before any of Chapter 4 makes sense, I have to give you at least the very beginning lessons in chemistry. So atoms are the smallest little Lego of material, of anything that you can see. So there are 118 types of matter. So there's 118 types of atoms, and those are called the elements. And if you think of one as a white Lego and one as a red Lego and one as a blue Lego, then you can take those Legos and assemble them together to build everything that you know. So all matter is composed of atoms of certain elements that are put together in certain proportions. So matter is anything that has mass and takes up space. So we're gonna look at the elements in a minute when we look at the periodic table, and they are made up of smaller components inside the atom. So this is a model of an atom. You have inside the atom the nucleus of the atom, and then surrounding that nucleus you have a cloud of electrons. The nucleus is made up of two subatomic particles, the proton, which has a positive charge, and the neutron, which has mass but a negative charge. The protons and the neutrons essentially have all of the mass inside that atom. The electron does have mass, but it's so tiny, it's like 2,000 times smaller in mass than the proton or the neutron. So you can almost think of it as just the mass being the nucleus. And the electron cloud, electrons are negative, equal to the positive charge. So inside an atom, if you have one positive charge, then you're going to have one negative charge in the cloud. If you have 100 positive charges in the nucleus, you're going to have 100 electrons or 100 negative charges in the cloud. So the positives and negatives will balance each other, but the mass is pretty much at the center of the atom. If you were to, in your mind, imagine a huge football stadium, like a pro football stadium, the Dallas Cowboy Stadium, if that were a picture of an atom, all of the mass in that atom would exist inside a marble placed on the 50-yard line of that football stadium. And the first row of electrons would be the last row of seats. So almost 100% of that atom is empty space, almost nothing, with a tiny little shred of matter. But yet that matter interacts with other matter to make everything that we know. So to review, you've got protons positive, neutrons neutral, inside the nucleus, and then electrons, which are in a cloud around the outside, and those are negative. So the symbols of the elements, we're going to look at the periodic table. There's 92 of the elements occur naturally. The rest of the 118 have been man-made. So think of it as a Jenga tower. If you can shove protons and neutrons and electrons together and they are stable for even a billionth of a second, we give ourselves credit that we have created an element that doesn't exist. Essentially, 92 of those elements are stable enough to not fall apart instantly. Radioactive elements do fall apart, but they fall apart very regularly. They're essentially deteriorating with energy and matter being lost all the time. That's what a radioactive means. But 92 of those elements in the periodic table you can dig out of the ground, or it's in gases or liquids on the Earth. So here's a periodic table. We'll study the periodic table later. We're going to see that they are in rows, and those rows are called periods. That's why it's called a periodic table. And in columns. Everything in the same column is going to behave similarly as they react together. So for instance, if you have H2O, which is 2 number 1s and 1 number 8, they will combine to form a molecule. Well, if hydrogen reacts with oxygen, underneath oxygen is sulfur, number 16. Hydrogen will also react with sulfur exactly the same way. Instead of saying H2O, you'd have H2S, and that's sulfur. It's a dihydrogen sulfide, which is the smell of rotten eggs. If you've ever smelled rotten eggs, that's the smell of it. They will combine the same. So you're going to have lots of information stored in this periodic table in terms of what combines with what energy is required to make those things happen, or what energy is released if two things are broken apart. So that we'll study at a later time. On the periodic table, too, is giving you some information based upon the subatomic particles. The atomic number is the number of protons. And so if I come back to the periodic table, these are listed in atomic order. So you have number 1, hydrogen, that's 1 proton. 2, helium, that's 2 protons, etc. And so it's going up incrementally in terms of protons. That's called atomic number. The mass number is everything that was massive. And if you remember, the electrons are so small that you basically don't count the electrons. So a mass number is all the protons plus all the neutrons in that atom. So in the case here of oxygen, it's 16. There are 8 protons, that's the atomic number, and then 8 neutrons add together to be 16. You're going to see that instead of 16, we've got 15.999. What you're going to see is that is a average of the different weights of oxygen. So you're going to have most of oxygen is going to be 8 protons and 8 neutrons, and that adds up to 16. You're going to see, since that the average is slightly less than 16, you're going to have some oxygen that have 8 protons and 7 neutrons. But you only have a little bit of that, and when it's averaged together, it's going to be closer to the 16. So we're going to see that those are called isotopes. And an isotope has the same number of protons. Okay, for instance, hydrogen has 1 proton, so 1, 1, and 1. But if you have different number of neutrons, it's still going to be hydrogen because that's defined based on its atomic number, its proton number. But the differing number of neutrons make, in this case, protium, deuterium, tritium, just heavier. That's all it is. It's still hydrogen, but it's heavier hydrogen. Those are isotopes. And that number 15.999 on oxygen means that they've averaged the isotopes, and almost all of them are going to be 8 neutrons, which gives you a mass number of 16. Some of these isotopes are radioactive, and I've already mentioned that breaks down. It's going to start emitting energy. So radioactive materials are unstable, and they're essentially falling apart. They're falling apart in terms of matter. They're throwing out matter, but they're also throwing out energy. And all of the man-made elements are radioactive isotopes, only they fall apart instantly. Most of the ones that are made in labs may only have existed for a zillionth of a second or something ridiculous. The electrons are thought to, or mathematically thought to exist in shells or energy levels around the inside of around the nucleus. And so you're going to see that they're in certain places. You'll have, if you have 8 neutrons, you're going to have a shell, first of all, of 2, and then a shell of 6. If you have, in this case, aluminum, you're going to have 3 shells. You're going to have a shell of 2, and then a shell of 8, and then a shell of 3. So these are going to be at different locations energy-wise, and these are called energy levels. And as you increase the levels, you're going to increase the size of that atom. That atom's radius is going to get bigger and bigger as you have more electron levels. Valence electrons are really important in chemistry. The valence electrons means the outside shell of electrons. So if in the case of, we just saw aluminum having 3 levels, you have an inside level, a secondary level, a third level. The third level would be its outside, and so its valence electrons in this case would have 3. The valence of the oxygen, there's 6 in its outside shell, so its valence shell would have 6. And then the hydrogen, it only has 1 cell, so its valence shell is its only shell, and it has 1. So the valence electrons we're going to see are the ones that actually combine with other atoms to form compounds. And then an ion is an element that's lost or gained electrons. So if electrons have been stolen from that and it turns out to be a positive, then, because remember, the electrons and the protons are the same number inside a neutral atom, and so if I lose electrons, I've lost negatives. That means I'm going to become more positive. So an ion that's positive is called a cation, and if you steal electrons and pull it to yourself and you gain more of a negative charge, then you have a negative, you're now a negative ion, and that's called an anion. Hydrogen and helium are the most abundant elements in the universe. They're the smallest. Most stars burn hydrogen. So that's the most abundant in the universe because that's where most of the stars are made out of. The crust of the Earth is a little bit different. Most of the rocks that we're going to see in the Earth's crust are silicates. And silicate is a combination of silicon and oxygen. So if you've ever seen quartz, quartz is a silicate. There's numerous silicate rocks. Glass, which is made out of sand. So all sand is a silicate mineral. And glass is simply melted sand, and so that would be a silicate. So in the Earth's crust, most of the elements that we see in the Earth's crust are going to be the combination of oxygen and silicon, which make up these silicon rocks.